Right now, there's an electron sitting in front of you. But here's the thing, it's not really sitting anywhere. It's everywhere and nowhere at the same time. At least, until you look at it. The moment you observe it, reality makes a choice. Not you. Reality. Welcome to quantum physics, where the universe doesn't exist until someone's watching. What I'm about to show you isn't science fiction. It's science fact. And it's so bizarre, so fundamentally wrong, according to everything your brain tells you about reality, that even Einstein refused to believe it. He spent the last decades of his life trying to prove it couldn't be true. He failed, because quantum mechanics is true, and it's absolutely insane. Let's start with the most famous and most disturbing experiment in all of physics, the double-slit experiment. The setup is deceptively simple. Take a barrier with two parallel slits cut into it. Fire particles, let's say electrons, at the barrier. Some electrons pass through the slits and hit a detection screen on the other side. Now, if electrons behave like tiny bullets, solid particles, you'd expect to see two bands on the screen, one behind each slit. That's just common sense. But that's not what happens. Instead, you get an interference pattern, multiple bands of light and dark, like ripples on a pond colliding with each other. This is the signature of waves, not particles. When waves pass through two slits, they spread out, overlap, and interfere, creating bright spots where peaks align and dark spots where peaks and troughs cancel out. So, electrons are waves? Okay, weird, but manageable. But here's where it gets truly bizarre. What if you fire electrons one at a time? Single electrons, separated by seconds, so there's no way they can interact with each other. Logic says, each electron must go through one slit or the other, not both, so you should get two bands again. But you don't. Even firing one electron at a time, the interference pattern still builds up. Dot by dot, electron by electron, the wave pattern emerges. How? How can a single electron interfere with itself? How can it know about both slits? The answer, according to quantum mechanics, is that the electron doesn't go through one slit or the other. It goes through both, simultaneously. In a state called superposition, the electron exists in multiple states at once, as a wave spread across space, passing through both slits, interfering with itself. But the moment you try to observe which slit the electron actually went through, the moment you place a detector at one of the slits, the interference pattern disappears. Suddenly, you get two bands. The electron behaves like a particle again. Observation changes reality. Not metaphorically, not philosophically, literally. The act of measurement collapses the wave function, forcing the electron to choose a definite position. This isn't a flaw in our equipment. This is how nature works at the quantum level. By now, you might be thinking, okay, that's weird, but electrons are tiny. Maybe weird rules apply to tiny things. The world I see, tables, chairs, cats, that's still solid and real, right? That's what physicist Erwin Schrödinger thought too, and he hated the implications. So in 1935, he proposed a thought experiment to show how absurd quantum mechanics really is. Imagine you put a cat in a sealed box. Inside the box is a vial of poison connected to a radioactive atom. If the atom decays, it triggers a mechanism that breaks the vial and kills the cat. If it doesn't decay, the cat lives. Now, radioactive decay is a quantum process. According to quantum mechanics, until you observe it, the atom exists in superposition, both decayed and not decayed. Which means, according to the math, the cat is both alive and dead at the same time. Schrödinger designed this scenario to be ridiculous. He wanted to show that quantum mechanics, taken seriously, leads to Absurd conclusions. A cat can't be both alive and dead. That's nonsense. Except quantum mechanics doesn't care what makes sense to us. The real question is, when does the superposition collapse? When does the cat become definitely alive or definitely dead? Some interpretations say, when you open the box and observe the cat. Until then, the cat genuinely exists in both states. But that raises another problem. What counts as an observer? Does it have to be a conscious human? What about a mouse, a bacterium, a camera? Other interpretations, like the many worlds interpretation, say the cat is both alive and dead, but in different branches of reality. When you open the box, the universe splits. In one branch, you see a living cat. In another, a dead one. Both versions of you are equally real, just in parallel universes that can never interact. Still others say, consciousness causes collapse. That observation by a conscious mind is what crystallizes reality out of quantum fog. No, one knows. A century after quantum mechanics was formulated, we still don't understand what observation actually means or why it has this power. If superposition is weird, entanglement is downright spooky. Einstein called it spookhafte Fernwirkung, spooky action at a distance, and he meant it as an insult because he believed it proved quantum mechanics was incomplete. Here's how entanglement works. When two particles interact, they can become entangled. Their properties, like spin or polarization, become linked. Measure one particle, and you instantly know the state of the other, no matter how far apart they are. Not because information travels between them, but because they're not really separate. They're described by a single quantum state. Here's the kicker. Before you measure, neither particle has a definite state. They're both in superposition. But the moment you measure one, it chooses a state, and the other particle instantly chooses the opposite state. Einstein hated this. He argued that the particles must have had definite states all along, hidden variables we couldn't see. The entanglement correlation was just revealing information that already existed. In 1964, physicist John Bell devised a test, now called Bell's inequality, to settle the question. If Einstein was right and hidden variables exist, the correlations between entangled particles would obey certain mathematical limits. They don't. Experiment after experiment has shown that entangled particles are more correlated than any local hidden variable theory allows. The particles really don't have definite states until measurement, and the measurement of one really does instantaneously affect the other, even across light years. Does this violate relativity? Can we use entanglement to send information faster than light? No. The results of quantum measurements are random. You can't control what outcome you get, so you can't encode a message. The correlation only becomes apparent when you compare results afterward using classical communication. But the fact remains, reality at the quantum level is non-local. The universe doesn't respect the separation between here and there the way we do. So what's actually happening? What does quantum mechanics mean? The honest answer, nobody knows. We have the math, we have the predictions, and they work with stunning precision. But the interpretation, what it all means, is still debated. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, says, particles exist in superposition until observed. Measurement causes wave function collapse. The observer plays a fundamental role in creating reality, but it doesn't explain what an observer is or why observation causes collapse. It just says, that's how nature works. Stop asking. The many worlds interpretation, proposed by Hugh Everett in 1957, says, there's no collapse. Every quantum possibility actually happens, but in separate, branching universes. When you measure an electron's position, you don't collapse the wave function. You just become entangled with it. One version of you sees one outcome. Another version sees a different outcome. Both are real. This solves the measurement problem by eliminating measurement. There's no special moment when superposition ends. Everything stays in superposition. We just can't see the other branches. The pilot wave theory, or de Broglie-Bohm theory, says particles do have definite positions, but they're guided by an invisible wave. The wave goes through both slits, and the particle surfs along it, creating interference. Observation disturbs the wave, changing the particle's path. This restores determinism, but at the cost of non-locality. The pilot wave has to connect everything in the universe instantaneously. The quantum Bayesianism or cubism interpretation says wave functions aren't real. They're just tools for calculating probabilities based on our knowledge. Measurement doesn't change reality. It updates our information. Each interpretation has defenders. Each has problems. And here's the truly disturbing part. All of them make the exact same predictions. There's no experiment that can tell them apart. We can calculate what will happen, but we can't agree on what's really happening. Let's bring this back to something concrete. What does the observer effect actually do in practice? Consider the Quantum Zeno Effect, named after Zeno's paradox. If you continuously observe a quantum system, you can freeze it in place. The wave function never has time to evolve because each observation collapses it back to its initial state. It's like the old joke, a watched pot never boils. Except in quantum mechanics, it's literally true. Or consider quantum computing. Traditional computers use bits, 1 or 0. Quantum computers use qubits, which can be 0, 1, or both at the same time thanks to superposition. While in superposition, a qubit can explore multiple solutions simultaneously. But the moment you measure the qubit to read the answer, the superposition collapses. You get one answer. The trick is to manipulate the qubits in such a way that wrong answers cancel out and the right answer is amplified. So when you finally observe, you're likely to get the solution. Observation is powerful and destructive. Then there's quantum biology. Evidence suggests that photosynthesis in plants uses quantum superposition to find the most efficient energy pathway. Birds may use quantum entanglement in their eyes to sense Earth's magnetic field for navigation. Life itself might exploit quantum weirdness, but it's fragile. The larger and warmer a system, the faster it decoheres, loses its quantum properties due to interaction with the environment. That's why we don't see macroscopic objects in superposition. They're constantly being observed by surrounding air molecules, photons, and heat. The quantum world isn't separate from the classical world. It's the foundation. But the moment you try to look closely, it slips away. So where does this leave us? Quantum mechanics has been tested billions of times. Every prediction has been confirmed. GPS satellites, MRI machines, transistors in your phone. They all rely on quantum mechanics. But we still don't understand what it means. Does reality exist independently, or does observation create it? Are you collapsing wave functions with every glance? Are there infinite parallel versions of you experiencing every possible outcome? We don't know. What we do know is this. The universe at its most fundamental level is not made of solid things. It's made of probabilities, potentials, and possibilities. The world you see, stable, definite, real, is an emergent phenomenon, crystallizing out of quantum fog through the act of observation. You are not passively watching reality. You are participating in its creation. Every measurement you make, every observation, every interaction, it all matters, not metaphorically, physically. The universe doesn't exist in a definite state until something interacts with it. And here's the final twist. You're made of quantum particles too. Your brain, your neurons, your thoughts, They're all part of this quantum dance, which means at some level you are in superposition too. So the next time you look at something and think, that's real, remember, it wasn't. Not until you looked. Welcome to quantum reality. It's weirder than you can imagine. And it's the only reality we've got.